the moment. So yeah, morning everyone. Welcome to the SWEP webinar on sizing and selecting brazed plate heat exchangers. My name's Adam Raymond. I'm the regional sales manager for the UK Northern Ireland at SWEP. I'm joined today by my colleague Elliot Miles. He's our lead business engineer for the UK. And we're just going to give you an introduction really to the basic principles on sizing and selecting heat exchangers. And within that, we're going to include an introduction to how heat exchangers work, because of course not everybody is experts in how our products are made and work. So we're going to give you just an overview of everything and hopefully good grounding that will give you some idea of how to size and select units in the future. So just to cover the agenda, we're going to do a company introduction to SWEP, who we are and where we came from, some contact information for the UK team and our dealer network as well. We then look at the heat exchanger applications and how they're constructed. At that point, I'm going to hand you over to Elliot, who's going to give you an overview of heat transfer knowledge, which includes things like the pressure drop considerations, what kind of temperature profile is ideal to be working with, and if you move outside of that, what are the kind of considerations that you need to be aware of. Elliot will then hand back to myself, and I'm going to go over some of the design software that we have. Some of you might be using that already, the BIM models that we can produce from there as well. And we also take a little look at large brazed heat exchangers for high capacity projects. We mainly do this because I think it's often seen that brazed is only really for smaller applications, but in fact it really is a good solution for bigger district energy projects, and we've proven that with some case studies which we'll go through as well. So SWEP was founded in 1983 in Sweden. Two entrepreneurs in a garage that really they were working a lot in the heat exchanger industry, and they saw brazed as the technology that would really adapt to the future energy needs. I mean, you could almost say they were sort of visionaries, you know, seeing how things would develop. And of course now with low temperature heat networks, heat pumps of course are really coming to the front of energy source, looking at other applications, heat recovery. So brazed, it's a really exciting time at the moment. Since 1994, we've been part of the Dover family. So Dover is a big corporation based in the States, and they have a lot of similar businesses such as ourselves. So we have a very nice corporate parent, if you will, that really believes in us and has supported us since they took us into their family. So we have operations all over the world. As I say, the head office in Sweden, so we have a factory in Landskrona there. We also have a factory and offices in Košice. And then moving to the east, we've got a factory and office in China and Malaysia. And then going back west, we've got operations in the States, manufacturing as well. So we're quite well positioned to look after our customers all over the world. We also have R&D facilities in all these key locations as well, serving all our customers. We've got around 1,000 employees, growing all the time. And yeah, it's a really, really interesting place to be at the moment. Just going to introduce you to the UK team. So there's obviously myself and Elliot. Joining us as well is our colleague Dave Gill. Dave looks after district energy segment. We've got Harriet as our customer service support team member, and she's really the sort of key in processing all the orders and keeping us all in check. We've got Greg as our business engineer team manager. He works very closely with Elliot, supporting myself and Russ, and of course Dave and Harriet with more technical aspects of the business and of course the customers as well. We're based in Didcot in Oxfordshire, and so you can reach us there and of course on our mobiles as well. And then supporting us, we've got our UK dealer partners. We've got 5 in total that giving us good coverage across the UK. These guys are all more technically based distributors, so they're there to support us and almost an extension of us in terms of supporting, you know, the eventual end customer. And so they're really a key part of our day-to-day activities as well. We cover a lot of different segments at SWEP. A lot of people may know us for gas boiler, heat exchangers, district energy and so on. There's a good chance some of you might have a SWEP heat exchanger inside the boiler at your house at the moment if you've got a combi boiler, or even if you're living in a development that's part of a district energy system. Very likely that you're close to a SWEP heat exchanger. But we cover a lot of other areas as well. Supermarket refrigeration, power generation, air conditioning, obviously more for warmer climates, and of course heat pumps as well. So for what is essentially one product, brazed heat exchanger, it covers numerous different applications. So again, it's really interesting for us to be working in all these different areas. And of course, we have to have the expertise to advise our customers and to work with them on their projects. So there's quite a lot that we do get involved with. So we're going to look at what is a brazed plate heat exchanger, how is it produced, and how does it work. So sorry, I skipped a slide there. Here we are. So this is the basic principle of a brazed plate heat exchanger. Essentially, you've got a hot and a cold media channel, and it's a simple heat transfer of energy. An example could be cold water, cooling hot engine oil, or district heating from an energy center, the primary network, some of you may know it as, being used to generate domestic hot water in a residential apartment or any other commercial setting. So here we can see the alternating, hopefully you can see this, the alternating layers with my mouse pointer of the different fluid channels. So we would have here the hot channel on this layer, and then the cold, and then the hot, and then that is repeated throughout the heat exchanger. And what these different layers do is they not only hydraulically separate the two different media types, be it engine oil and water or water, they allow the transfer of heat as well. So we'll just cover now how the actual heat exchangers are constructed and produced. So here we've got the basic structure of a plate heat exchanger. We've got the channel plates in the middle. These are actually the ones that are containing the different fluids, separating them. You'll notice the herringbone pattern here. This is actually providing some resistance within the channel plates, and that's what allows us to kind of manage and manipulate the heat transfer. So we can change the angle of these chevrons here and the shape of them, depending upon the application. Does it need high resistance, or if pressure drops are concern, do we need to look at low resistance as well? These are built automatically. These plates are stacked together in the factory on the production line. We then have the front and back cover plates. These provide additional support and stability. So for applications where there's vibration and stress, it gives mechanical strength to the heat exchanger. We then have the connections as well, which we'll cover a little bit more in detail later. Generally, these are fitted to the front of the heat exchanger. However, depending upon the heat exchanger type or indeed the application and customer preference, we could, for example, have 2 connections here on the front and also 2 on the back. Once the heat exchanger has been assembled according to the design specification, number of plates, plate pattern, connections, and so on, it then goes into the furnace and is brazed with usually a copper brazed material, and it's then tested. Every single unit is pressure tested to design pressure and beyond, and then they're labeled and packed and sent out. So it's quite a rigorous production process that we go through for each and every single heat exchanger. So just covering a little bit more the materials that we use, we've got mainly it's stainless steel 316 and 304 for the channel and the cover plates. Brazing material, predominantly copper, but for more demanding applications, for example, if there's corrosive fluids, aggressive gases and so on, then we also have the option of looking at nickel brazed and stainless steel brazed as the brazing material. An example of this could be ammonia heat pumps, for example, where the copper brazing would be corroded pretty quickly. So we generally have to look at stainless steel in this kind of application. Another interesting innovation that we have at SWEP, some of you might have seen this at the CIBSE presentation I did a few months back. We have an innovation called Celix, which is basically it's a bonding of silicon dioxide to the inner surfaces of the heat exchanger. And what this does is it actually protects not only the brazing material, but also the stainless steel channel plates. And this is really enhancing the durability and lifespan of the heat exchanger. The main application we developed Celix for was tap water in parts of Central Europe where they've got particularly aggressive water. Perhaps it's open source, varying compositions, and even stainless steel units were corroding and failing pretty quick. So Celix is a really nice solution. It's always evolving and developing, and we're looking at applications other than tap water for that. So these are just the main materials that we're using at the moment for our heat exchangers. In terms of connections, we have pretty much connections to suit most applications. In HVAC, the most common would be an externally threaded or a DIN flange. But then for other circumstances, we've got internal threads, SE flanges for automotive applications and also for the rail industry. Victolic, I'm not seeing it used so much in the UK, but it's very common in Europe. We also use that to join heat exchangers together if we're putting more than one in series. And then, of course, we have solder weld for the refrigeration industry. So we talk about different executions with heat exchangers. There's a lot of different executions. I'm just going to cover the 2 basic ones here. The first one is what we call single pass, and this is what we would commonly see inside, say, a gas boiler, for example. And by single pass or one pass, hopefully you can see my mouse pointer here, but if you see the blue channel going in through the connections, you'll see it dropping down, and then the hot side is going up in the opposite direction. So the 2 different medias are just passing each other once, and that's allowing the transfer of energy. In a multi-pass unit, we have that happening more than once. So in this case, we've got a 2-pass unit. And what that basically allows us to do is to create essentially a longer heat exchanger, but in the same compact shape. But you'll notice that the connection orientation is slightly different. And this is a feature of multi-pass units, that we have connections on either end. It's not so much an option, it's just the way that they work. So hopefully that's given you a good kind of basic grounding into heat exchanger design, manufacture, a little bit about SWEP and where we come from. I'm now going to hand you over to my colleague Elliot. So Elliot, I'm just going to give you control. So let us know when you've got it.
Okay, thanks for that, Adam.
Pleasure.
So I'm just going to cover a bit more of the technical details concerning a brazed plate, starting with some heat transfer knowledge. So it's first worth mentioning that heat transfer efficiency can be affected by the flow arrangement. So there's two possible arrangements that we typically see. We have countercurrent on the left, which is when the two fluids enter the heat exchanger at opposite ends, and hence the flow is in the opposite direction. This is found in the vast majority of applications we see, since it allows for an internal temperature cross of the two fluids. On the right, we have co-current, and this is where the flows enter at the same end of the heat exchanger and are therefore parallel. It's actually less efficient than in countercurrent because the exit temperature of the colder fluid can't be greater than the exit temperature of the hot fluid. So we move on to something called thermal length, and this is defined as the change in the temperature of one fluid in relation to the actual temperature difference between the two fluids. So the graphs here are showing the different thermal cases that can occur, and that would require different plate patterns to meet the design whilst avoiding oversizing. So a low theta pattern is generally for an easy case, which is where you'd have a small temperature change in one of the fluids or both fluids and a large temperature difference between the fluids. Then we move into a more difficult thermal case, which can be covered by a high theta pattern. So this would be where we have a large temperature change, but a small temperature difference between the two fluids. And then finally, we may see something more tricky, where the change in temperature on each fluid might be different. And then we have a changing temperature difference between the two sides over the heat exchanger. And this can be covered by an asymmetric design, where we would have different theta patterns or perhaps a set of wide and narrow channels. So we address this with the pressing of the plates, and this characterizes the heat transfer performance, or what we call thermal length. So a wide chevron angle shown at the top is a high theta pattern, and that's for cases that are difficult and require a large thermal length. On the other end of things, we have an acute chevron angle, or a low theta pattern, and this is where a small thermal length is required. A high theta pattern can give the best performance, although it may be at the expense of a higher pressure drop than a low theta pattern. In some of our BPHE models, a high and low theta pattern can actually be mixed to give a medium or what we call a mixed theta pattern. SWEP have developed a plate construction which can cover tricky thermal cases. You will notice that some of our models are followed by AS, which means asymmetric. These models typically have a narrow and a wide side, and this can be seen in the diagram at the bottom here. The top diagram actually shows a symmetric plate where the channel volumes are even. So now to move on to some pressure drop considerations that need to be considered in the selection of brazed plates. So first of all, we have turbulence against pressure drop. So the resistance in the plate channel actually creates turbulence, and this is necessary for high heat transfer coefficients. A resistance to the flow creates pressure drops, and so there's always actually a trade-off between good heat transfer and pressure drop. For a good design, the fluid velocity must be high enough to give fully developed turbulent flow. When the flow is turbulent, we also see high values for shear stresses, which creates a self-cleaning effect, and that can greatly reduce any fouling and scaling. For lower velocities, careful consideration has to be given to the impacts on performance, efficiency, and also risk of fouling or scaling. Our Celix technology can help to mitigate against this risk. So now considering pressure drop against heat transfer. So as previously mentioned, in order for the heat transfer to occur, the payment is actually pressure drop. Therefore, what we want is for the pressure drop to occur within the plate channel itself where the heat transfer happens, and to minimize the pressure drop elsewhere. The ports must be big enough as to not create a large restriction to the flow. And as a rule of thumb, we say that the pressure drop in the ports must not exceed 1/3 of the overall pressure drop. This also allows an even flow distribution, which keeps the temperatures stable. So now some temperature profile considerations. So what is a realistic LMTD? The required temperature difference between the two fluids, as shown on the left here, is called the logarithmic mean temperature difference, or LMTD, and this has a direct impact on the size of the heat exchanger. The relationship between LMTD and area is inversely proportional, and so a decrease in LMTD leads to an increase in the required surface area, and hence the physical size and also cost of the heat exchanger. As the LMTD is reduced, there's a diminishing return from additional surface area below a temperature difference of around 1 degree Celsius. This means that from a system design and capital cost perspective, it can be beneficial to keep the LMTD above 1, and SWEP may even advise in some cases to keep it above 3 if possible. So how can we address the temperature profile issue? Increasing the LMTD not only allows for a smaller heat exchanger to be used, but also allows for higher channel velocities and hence better performance and reduced risk of fouling. Since the heat exchanger is designed for peak load conditions, which may rarely be experienced, it may be beneficial to apply load profiling, such as the European Seasonal Energy Efficiency Ratio. Applying such load profiles to the selection of the heat exchanger adapts the LMTD for the peak load design condition to give a heat exchanger with less surface area. The effects can be highly beneficial, reducing capital costs and operating costs, since the heat exchanger will be smaller and provides turbulent conditions for a greater period of the year. The example here shows the application of the ESEER profile, which reduces the heat transfer area from 207 to 107 meters squared. The 207 meters squared selection provides turbulent flow down to around 60% of the peak load, whilst the 107 meters squared selection can provide turbulent conditions down to 25% of the peak load. There's also a reduction in capital costs of around 40%. Yet the increase in the LMTD is only 0.4 degrees at the peak load. The original 1 degree LMTD that was specified would still be achieved most of the time. I'll now hand back to Adam we will talk about some of SWEP's high capacity brazed plates.
Thanks, Elliot. That was really great. Hopefully everyone there, took on the knowledge that you were passing on. Yeah, so I'm just going to get to the correct slide, so bear with us. Okay, great. So, as I mentioned earlier, a lot of people associate brazed with smaller applications, gas boilers perhaps, HIUs, but in fact, we do see them a lot used in larger applications, district energy in particular, in the UK and Europe. So I just want to go through a little bit some of the kind of design considerations and how a large brazed unit can not only work, but work particularly well compared with some other technologies. So we developed one of our largest heat exchanger, the B649, specifically for the district energy market. And really, we can offer quite high capacities, up to 10 megawatts in this particular unit. And we can also configure it to other applications as well, to other configurations. So here we've got the modular concept. So you can see we've got it in serial and parallel configuration. So not only does it have a very high capacity as a single unit, but we can, with our design tool, we can link it together. And so you get all the benefits of a compact unit, but in a modular solution. So of course, there's a lot lower footprint relative to the kilowatt load output of the heat exchanger compared with, say, gasket technologies. And as you'll see in some of the case studies a little bit later on, the compact size makes it a bit more maneuverable on site. One of the questions we get asked about brazed, one of the many questions, but in particular with large heat exchangers, is how do we add extra capacity? This is, of course, one of the features of a gasket plate heat exchanger, that you can add more plates if the system is expanding over time, additional capacity is required. Excuse me. So we can't open the brazed heat exchanger. So the solution here is that we have what we call a booster BPHE. So this is basically just configured to the additional capacity that's required, whatever that may be. And of course, providing the space to move the existing heat exchanger back, which of course you would need with any other solution, then we can add just a small extra brazed plate pack to give you that extra capacity. And of course, you've got a 100% tested, pressure tested, certified heat exchanger that just simply bolts on. Very little extra, labor work required, no pipework modification. It's just basically pushing the existing unit back and slotting in this booster unit. So we can address that additional capacity on the large scale heat exchangers quite well. Another question we get asked is cleaning of heat exchangers. So in this short video here, you'll just see how that's addressed. Again, brazed units can't be stripped, but our philosophy is that we would always push people down the road of cleaning in place. Of course, there needs to be some valve and tapping configurations put in. An option could be to actually just remove the heat exchanger and put it to one side and do the cleaning in place that way. But it's a very effective solution. Of course, there's no requirement for stripping, regasketing, the associated cost and labor involved in doing that. So it's a very effective solution for cleaning heat exchangers. And of course, I think the obvious thing to mention is prevention. It is, of course, better to prevent than to cure. So we always advocate for good water quality, the monitoring of the water quality, and also, just the installation and commissioning good practice should be observed here. But we've got there is the capability of cleaning large heat exchangers. So I'm just going to cover our design software. Hopefully some of you are familiar with this, perhaps you're using it already. SSP has been around since the kind of mid to early 90s, started out as a DOS command program. It's now developed significantly. We've got the we've got the desktop-based version, which we call SSPG8. That can be downloaded from the SWEP website. It looks a little bit something like this. When you open up the page, you get multiple selections of different calculation windows, such as single phase, condenser, and so on. The ESSER calculation that Elliot mentioned earlier, that's also available to select in SSP. And for that, you would look at the district energy option. So that gives you the capability to design a heat exchanger with ESWR factored in already. So that's quite a really nice feature. We've recently launched a web-based version of SSPGA, which we call dthermx. This is useful for people that perhaps have to work on different devices and they just want one common portal, if you will. Or if there's restrictions on downloading programs with your IT providers or IT staff. So dthermx is a really nice web-based solution. It replaced a previous web-based version that we had, and it's much better. It's got pretty much all the features of SSPGA. We're developing it all the time, and this is a really nice solution for people that can't or don't want to install on the machine. Another example could be if you're running an Apple Mac, because SSP is only for Windows at the moment. So just to show you a little bit the calculation window in SSP, worth mentioning that if anybody does have SSP and they're using it and maybe they're not quite comfortable or they would like to know a little bit more, we do offer free of charge training sessions through Teams or Zoom, whichever you prefer. And that could be with Elliot, my colleague Greg, or myself, or Russ. And we can just guide you through sizing and selecting, or with SSP, or even dthermx. But it's a fairly straightforward and intuitive process. You simply enter your fluids here, fluid side 1 and 2, put in your temperature profiles, and then you get a list of heat exchangers according to price and performance rating. But again, a more in-depth session is available to anybody that's listening or anybody that you know, just to give you a better understanding of how to use it. All our heat exchangers are available with BIM level 2 files. These can be ordered directly from SSP and dthermx. So if you've done a design, you've set everything up and you know this is the unit that you want, you can go and directly order the BIM model, which is a really nice feature. Of course, you can always contact us if there's an existing unit that you have or you'd like a different drawing that's not available there. So just to run through some case studies, and these are quite nice examples of where we've used the large brazed heat exchangers on some interesting projects. So this is the Tele2 Arena in Sweden. It's one of the more well-known football arenas in Stockholm, and they had a plan to expand the kind of use of the stadium beyond football. So they wanted to turn it to a multi-sport arena. So they needed to be able to turn it from a football stadium with obviously grass as the pitch, and then to put ice on the ground. So they had quite a, you can imagine, quite a high capacity cooling system that they needed to do that. And so they talked to us at SWEP, my colleagues in Sweden, assisted them with the design. And so we had 8 of our B649s as the interface between the cooling system, energy source, and of course the eventual cooling on the pitch. And Again, the nice feature with the braze pack, the compact size, it's fitting through a standard door pretty easily. You can see here it can be a one-man maneuver. Of course, he's got a pallet truck to help him with the lift and some lifting support equipment there as well. We've got DN400 headers. You can see here we've got multiple units connected together. And then this is the result, green grass to hard ice, which is quite impressive, I think, and really enabled with the technology of our heat exchangers with the brazed concept. So I'd like to thank everyone for listening to the webinar. You've probably had your fair share of lockdown learning over the past year or so, so we do appreciate your time. I'm just going to see if there's any questions that have come in.